Welcome to today's deep dive. I want you to start by just imagining you're trying to paint a room in your house. You've
Right.
got your colors picked out, you're ready to go, and you put down that classic blue painter's tape to protect the baseboards.
Right, the really crucial step.
Exactly. So you paint a beautiful, crisp line, but then every single time you pull the tape off to move to the next section, the tape just rips off the fresh paint you just applied right along with it.
Oh, man.
Yeah, and you try it again, maybe, like pulling a bit slower, and the exact same thing happens. The very tool you are relying on to keep your work neat is actively destroying the work you just did.
That is a remarkably frustrating visual to start us off with. I mean, it makes my chest tight just thinking about it.
I know, right?
But I have to admit, it perfectly captures the underlying tension of what we're looking at today. Because when you try to fix one part of a system, and that fix inherently breaks another part,
Yeah.
you're stuck in this logical loop.
And today, we are going deep into a loop exactly like that, but it's happening inside the software you use every single day.
Yeah.
A lot of you listening might not be programmers, but our mission today is to promise you this incredibly satisfying aha moment about a deceptively complex logic puzzle that just hides right under your nose.
It really does.
Our source material is an entry from June 22, 2026. It's a post titled Notes on Haskell Programming, Part 167 by a developer named Ang. And the specific topic is two-pass sentinel string replacement.
Which I know two-pass sentinel string replacement sounds incredibly dense on the surface.
It's a mouthful.
Right, but the underlying problem it solves is entirely universal to anyone who uses a computer.
I completely agree. We're going to explore how developers use these clever, almost magical hide-and-seek tactics to prevent software from tripping over its own code. But honestly, when I first read the title of Aaron's post, I had to stop and ask myself, Part 167.
Yeah, that's a lot of parts.
Right. Why is a simple task like finding a word and replacing it suddenly requiring a 167-part blog series?
It's the most natural question to ask. We think of find and replace as a fundamentally solved problem, right?
Exactly.
You hit Control-F or Command-F on your keyboard, you type a word, you type a new word, and you hit replace all. It feels instantaneous, and it feels perfectly reliable.
Right, like magic.
But the reality, though, is that this simplicity is a total illusion. The computer is actually performing this highly precarious high-wire act behind the scenes.
Wow.
So to truly understand why a developer like Ang is writing Part 167 of a series, we need to look at the specific environment they are building in.
Let's unpack that environment then. Ang is working on a custom project, right? It's a console application called XS2 ebook.
Essentially, yeah, it's a structural conversion tool.
So the app's entire job is to take standard, plain text files, just your basic TXT documents, and convert them into what's called a Typst document. Typst is spelled Typst for those wondering.
Right.
And eventually, those Typst documents are compiled by the system into standard PDF files.
And that conversion process involves a lot more than just, changing the file extension at the end of a document.
Of course.
It's about automatically adding architecture to the text. Like, think about when you read a good PDF, especially a technical manual or a textbook.
Right.
It has a robust index at the back. It has those clickable bookmarks that jump you to specific chapters.
Very handy.
Yeah. And Ang wants this XS2 ebook program to generate that index and those bookmarks without any human intervention at all.
Which means the software has to read through the entire plain text document, locate specific keywords that belong in the index, and wrap them in special Typst formatting code.
Exactly.
So if the keyword is, say, the word apple, the program needs to find the word apple and replace it with hashtag index open bracket apple close bracket.
That's the exact mechanism. The hash symbol, the word index, and the brackets act as this signal flare to the PDF generator.
Okay.
It tells the compiler, hey, this word is important, categorize it, and put it in the back of the book.
Got it. Which brings us to the core villain of our story. In the source material, Ang refers to it as ambiguous overlapping substitution.
Yeah, that's a very technical way to put it.
I just call it a mouthful. But programmers also know it as a collision error, right?
Collision error provides a much better mental image. It happens when two rigid rules just crash into each other in the exact same physical space.
So I want to share the exact example Ang uses in the post, because this is where the problem really clicks.
Oh, it's a great example.
Imagine we have a basic sentence in our text document that just says, I love foobar too. Just that simple sentence.
Okay.
Now, we have a master list of keywords that our program needs to index. In our list, we have two specific keywords, the word foobar and the shorter word foo. FOO.
It's the absolute perfect trap. Foo and foobar.
To a human brain, if I ask you to find the word foo in the word foobar, you intuitively know what I mean, right? You understand context.
Of course.
You easily distinguish between the two concepts. But a computer doesn't read concepts. A computer acts more like a blind bulldozer. So what is actually happening mechanically when it hits that sentence?
Right. So if we zoom in on how a machine processes data, it just sees an array of characters. It registers the letter F, then the letter O, then B, A, R.
Okay.
It has absolutely zero comprehension of what foo means in the real world. It just matches the sequence of letters you asked for.
The bulldozer just drives straight.
Exactly. So when that bulldozer rolls over the sentence, I love foobar too, and its instructions are to look for both foo and foobar, it encounters a massive logical roadblock.
Ah.
Which set of instructions is it supposed to execute? Because the literal sequence for foo is physically sitting right inside the sequence for foobar.
Right. And this leads directly to the two massive logical dead ends that Ang outlines in the post. These are the two failure modes.
Yeah.
This is where the painter's tape starts ripping the paint off the wall. Let's look at the first one.
So Ang calls this first trap the shortest first failure.
Meaning, the program decides to tackle the problem by looking for the shortest words in the keyword list first.
Right.
In our case, it goes hunting for foo before it even considers foobar.
So the bulldozer rolls through our sentence, I love foobar too. It's scanning for FOO. It finds those exact three letters right at the start of the word foobar.
Okay.
It immediately stops, follows its programming, and replaces foo with the Typst markup.
So it changes the letters foo into hashtag index bracket for close bracket.
It does. But we have to look at the collateral damage to the rest of the sentence.
Oh, right.
The original sentence was, I love foobar too. The new modified sentence is, I love hashtag index bracket foo close bracket bar too.
Oh, wow. It completely chopped up the original word.
Exactly.
The bar part of foobar is just left hanging out there at the end of the bracket like a typo.
It's orphan text. And this creates a catastrophic failure for the program as a whole, because the program still has to complete its second task. It still has to look for the longer keyword, foobar. But when it sweeps through the document again, foobar simply doesn't exist anymore.
Because it broke it apart.
Right. The text is now hashtag index foobar. The sequence FOOBAR has been permanently destroyed. The program completely misses the index for foobar because of its own previous action.
The painter's tape ripped the paint off. By successfully fixing the short word, we unintentionally destroyed the long word.
That illustrates the shortest first failure perfectly.
Now, you might think the solution is incredibly obvious, just, reverse the order.
What?
Which brings us to Ang's second failure mode, the longest first failure.
And I actually find this one even more insidious because it initially looks like it works.
Right. So we instruct the program to be smart and look for the longest words first. It takes our sentence, I love foobar too, and it sweeps for the longest keyword on the list, foobar.
And this time, it finds it cleanly. It successfully replaces the entire word foobar with the Typst markup. The sentence is updated to, I love hashtag index bracket foobar close bracket too.
We celebrate, right. I mean, we got the long word index without chopping anything up.
Right, but hold off on the celebration
Oh.
because the job isn't done yet. The program still has that second keyword on its master list. It still has to scan for the shorter word foo.
So it sweeps the new sentence. The sentence is now, I love hashtag index foobar too. The program is blindly scanning for FOO. And wait, it finds it.
It finds it.
Yeah.
It finds the sequence FOO sitting right inside the markup it just finished writing.
Oh, no.
Yeah, it looks inside the brackets at the word foobar and says, aha. Here is FOO. And because it's a blind bulldozer, it executes its job again. It replaces that foo with hashtag index bracket foo close bracket.
Inside the first index.
Yeah.
So the final output becomes this chaotic, nested mess. It reads, I love hashtag index bracket foo close bracket bar close bracket too.
Which is completely invalid code. When the Typst compiler eventually tries to read those nested brackets, it will just throw a syntax error, and the entire PDF will fail to generate. The program literally tripped over its own shoelaces while trying to walk forward.
I have to pause here and just push back on this on behalf of everyone listening.
Sure.
Because right now I'm thinking, why are we treating the computer like it's this incredibly stupid? Why not just tell the program to ignore any text that's already inside brackets?
It makes sense to ask that.
Right. Why not give the bulldozer a rule that says, hey, if you see a hash symbol in a bracket, just lift your blade and skip that part? Why can't it just read the context?
That is the absolute most natural human response to this problem. I mean, if we were editing a document by hand, that's exactly what we would do. We'd see the brackets, and our brains would instantly categorize that as code, not text.
Exactly.
But this raises a really fundamental point about how computers process text efficiently versus how they process it inefficiently.
Because giving it context sounds trivial to us, but it's actually a heavy lift for the machine.
It is an exponentially heavier lift. When you try to add rules like read the context or check if you are currently inside a bracket, you are forcing the computer to maintain a constant awareness of its state.
Okay.
And to do that, you end up having to use incredibly complex algorithms, usually involving something called regular expressions or regex.
Oh, regex, which I know is a term that makes even seasoned developers break out in a cold sweat.
Oh, absolutely. Regex is powerful, but it's notoriously difficult to read and maintain.
Right.
To solve this specific collision, you'd have to write a regex rule with complex things called look-aheads and look-behinds. You're essentially telling the program, okay, before you replace this word, stop. Look 20 characters to your left. Do you see a bracket?
Oh.
Now look 20 characters to your right. Do you see a closing bracket?
That sounds exhausting just to say out loud.
And it's exhausting for the computer's processor, too. Every time you add a conditional rule, the program gets slower. It requires significantly more memory.
That makes sense.
If you're processing a massive, 1,000-page textbook with tens of thousands of keywords, a context-aware regex search could take an agonizingly long time to run. Plus, it introduces just endless edge cases for bugs.
Yeah.
In software development, and especially in pure functional programming languages like Haskell, which Ang is using, the ultimate goal is to find a fast, elegant, dumb solution.
I really love that phrasing, the pursuit of a dumb solution.
It's the holy grail.
Uh-huh.
You don't want the bulldozer to have to stop, calculate its surroundings, and make complex decisions every 3 feet.
Thinking is slow.
Thinking is slow. You want the bulldozer to just drive straight at maximum speed. So the real challenge is how do we alter the environment itself so that a dumb, straight-driving bulldozer naturally avoids the trap without needing to be taught about it.
So we have to stop the collision without teaching the bulldozer how to drive around it.
Yes.
Since both the shortest first and the longest first approaches actively create broken code, the core realization here is that the program simply cannot format the text and search the text at the exact same time.
It's exactly.
The very act of formatting is what creates the collisions that break the subsequent searches.
The two actions have to be entirely decoupled from one another.
And this leads us to Ang's recommended solution. It's a technique called a two-pass sentinel string replacement, or, as Ang much more colorfully calls it, hide and swap.
Hide and swap is brilliant terminology.
Yeah.
But before we can execute the hiding phase, Ang emphasizes that there is a vital prerequisite step. We have to organize our data.
Right, we have to sort the keyword list by length.
Longest first, specifically. We have to guarantee that the program looks for foobar before it looks for foo to prevent that orphan text issue we saw in the shortest first failure.
Right.
Ang actually shares the exact snippet of Haskell code used to achieve this.
The code snippet in the post is, let me see, sort big open parenthesis, flip $sign comparing TL.length, close parenthesis.
That TL.length part is the really crucial piece there. It's evaluating the text length of every keyword and arranging them so the most complex, longest words are at the very top of the pile.
Okay, so our keyword list is sorted. Now we introduce the star of the show, the sentinel. We keep saying two-pass sentinel. What exactly is a sentinel in the context of computer programming?
Well, a sentinel is a highly unique artificial placeholder string. It's a sequence of characters meticulously engineered by the developer so that it would absolutely never, ever appear naturally in the real text of the document.
It's like an alien word dropped into an English dictionary.
Exactly like that. In Ang's example, the sentinel used is \NUL space K0 space \NUL.
Let me just spell that out for you listening. It's \NUL space K0 space \NUL.
Let's break down why that specific string is chosen too. The \NUL represents a null character.
Okay.
Now, a null character isn't a space. It's not the number 0. It is a non-printable control character from the earliest days of computing. It basically tells the system, this is a fundamental void.
Wow.
You literally cannot type a null character on a standard keyboard while writing an essay about apples or foobar. It is chemically impossible for it to exist in the author's original manuscript.
So it's foolproof.
It is a completely artificial, impossible tag.
This entire concept, it sounds exactly like using a coat check at a crowded museum.
Oh, I really like where you're going with that.
Yeah.
Let's unpack the museum visual.
Okay, so imagine you walk into a museum in the dead of winter. You're wearing this massive, heavy, complicated winter coat.
Right.
That coat is our long keyword, foobar. You do not want to carry that giant coat around the delicate exhibits because it's going to knock things over. It's going to cause collisions.
Makes sense.
So what do? You go to the front desk and you trade your massive coat for a weird little numbered plastic ticket.
And the numbered ticket is the sentinel.
Yes.
Yeah.
The plastic ticket is our /NUL, K0 /NUL. Now, you can walk freely around the museum holding this little ticket. Nobody else in the museum is going to accidentally wear your plastic ticket.
No.
Nobody is going to bump into you and accidentally sew a patch onto your plastic ticket. It is completely immune to the environment.
Right.
Then, later, when you are completely done with all your museum wandering, when the program is done with all its searching, you go back to the desk, hand over the plastic ticket, and trade it back for your completely unmessed up coat.
That is a phenomenal analogy because it maps perfectly to the mechanics of the algorithm. The first pass through the document is the act of handing the codes to the attendant. The second pass is trading the tickets back.
Let's actually execute this in the code then. Let's walk through the exact two-pass process on Ang's test sentence so we can see this code check working in real time.
All right, we start with our original unformatted sentence, I love foobar too.
Pass 1 begins. The hide.
The program looks at its newly sorted keyword list. It grabs the longest one, first foobar. It sweeps the sentence, locates foobar, and immediately swaps it out for our sentinel ticket.
So the sentence, I love foobar too, suddenly becomes, I love /NUL K0 /NUL too.
And this is where the sheer genius of the hide and swap reveals itself. The program moves to the next keyword on its list, the shorter, problematic word, foo. It sweeps the sentence looking for FOO, but the sentence is now, I love /NUL K0 /NUL too.
The word foo is simply gone.
Exactly. The text foo is temporarily locked away inside the sentinel ticket at the code check.
So the dumb bulldozer drives right past it.
It safely skips it without needing any complex regex rules. There's no collision. There's no nested Typst markup.
That's amazing.
The program finishes the entire first pass, sweeping through the whole document, swapping every single keyword it finds for a uniquely numbered sentinel ticket, K0, K1, K2, K3, and so on.
So by the end of pass 1, our text document probably looks like absolute gibberish to a human reader. It's just flooded with these weird null characters and sequential K numbers.
It looks like gibberish, yeah, but it is highly structured, mathematically perfect gibberish. Which brings us to pass 2, the swap.
The museum is closing, and it's time to get our coats.
The program initiates one final sweep through the document. But this time, it ignores the natural text completely. It doesn't care about foo or foobar or apple. It is only looking for the sentinels.
It scans specifically for /NUL K0 /NUL.
When it finds that exact ticket, it caches it in, it swaps the sentinel out, and replaces it with the final Typst markup we wanted all along.
It swapped the sentinel for #index bracket foobar close bracket.
And just like that, the sentence transitions from I love /NUL K0 /NUL too directly to I love #index bracket foobar close bracket too.
Perfect.
It's completely clean. There are no nested brackets. There are no ruined substrings.
The elegance of that is just incredible to me. You solve a complex formatting collision not by adding more complex formatting rules, but by utilizing a clever trick of ordering and hiding.
Exactly.
You just take the fragile data off the board completely while the heavy machinery does its work, and then you put it back when the coast is clear.
It is the absolute essence of good software design, keeping things modular and pure. Now, Ang does make a point to mention that the actual Typst code used in the real XS2 book production environment is a bit more complex than our simple #index example.
Right, Ang mentions the real production code looks something like #index open bracket keyword close bracket, #link open parenthesis angle bracket index angle bracket close parenthesis open bracket keyword close bracket.
Right.
It's creating a structural index entry and a clickable hyperlink simultaneously.
Which just reinforces why the Sentinel method is so mandatory here. If the markup is that long and involves that many special characters and brackets, the chances of a shorter keyword accidentally colliding with the markup code is just astronomical.
And also dives a bit into the specific Haskell execution of this. The logic utilizes a function called applyIndex, and there's a snippet in the post featuring something called fold replace with Typst.
Ah, yes.
For those of us who have never touched Haskell, what is folder actually doing in practice?
So folder is a very powerful standard concept in functional programming. stands for fold right. The easiest way to visualize it is to imagine rolling a snowball down a hill.
Okay, a snowball.
The fold operation takes a starting value, in this case, our plain text document, and a list of items are keywords. It systematically rolls through the list, applying the replacement function for each keyword, and accumulating the results into one final updated document. It basically folds the list down into a single, completed output.
Aang actually mentions that this apply index function could be refactored for readability in a future post.
Yeah, we might be seeing part 168 soon. But regardless of how this syntax gets refactored, the underlying architectural logic, the simplified hide and swap, remains the core solution. The architecture of the fix doesn't change. Yet the code gets prettier.
It's just a brilliant approach. Let's zoom out and summarize this journey we've been on.
Just do it.
We started with a really messy collision of words in a simple sentence. The word foo crashing catastrophically into foobar.
We navigated the obvious traps. We saw how a shortest first approach destroyed the longer words, leaving us with orphan text like #index_foobar.
We saw how a longest first approach created terrifying nested loops where the program blindly indexed its own index, creating #index_foobar.
We also explored why trying to give the computer human-like context using regex is a trap that leads to massive complexity and slow performance.
Which finally brought us to the incredibly elegant two-pass sentinel string replacement method, the hide and swap. We sort the list by length, we trade the fragile words for uncollidable plastic tickets, our sentinels, and once the bulldozer is parked, we swap the tickets for the final formatted code.
It really is a masterclass in lateral thinking.
Well, it truly is. It takes a problem of overlapping physical space and solves it through time. First pass, then second pass.
All through time. I absolutely love that framing.
And it leaves me with a final thought for you, the listener, to mull over. Because this isn't just an abstract lesson about Haskell or generating PDFs.
No, not at all.
This hide and swap trick is foundational to modern computing. I want you to ask yourself where else in the digital systems you use every single day, from your word processors to your web browsers, your messaging apps, or even your video games, where else are invisible sentinel placeholders silently holding the place of complex data?
Yeah, we're everywhere.
They are allowing seamless formatting to happen right under your nose without you ever seeing the magic trick. Next time you hit replace all, just think about the invisible coats being checked in the background. Stay curious, everyone.